Hello students, welcome to the second experiment of AECD lab, which is the design of current mirrors. So now let us get into the objectives of this particular experiment. As a very first objective, we will be evaluating the output impedance of the MOSFET under different channel lengths, but having a width which is equal to 10 micrometer. Now you could note that we are not using the default width of 2 micron here, but rather we have increased the width to 10 micron. And the reason for this huge value of the width is to reduce the mismatch errors between the transistors that we will be using for the current mirror structure. Now the details of these mismatches would be discussed during the class. The second objective is to design the current mirrors using different topologies. Basically the first one being a basic current mirror, the second one is a cascode current mirror, and the third one is known as a high swing cascode current mirror. Now in each of these current mirror design we'll be using a reference source current whose value would be like 100 microamperes. Okay. Now once we design this, we'll be evaluating the output impedance of the current mirror, as well as we'll be evaluating the minimum output voltage that the transistors that are used in the current mirrors can stay in the saturation regime. Okay, so these are the objectives that we are going to discuss, and let us get into the cadence. Now here is the circuit setup that is meant to perform our first objective. Note that the width and the length of this transistor is defined with a variable of capital W as well as capital L, and the VDC of this VGS is again defined with a variable which is VGS, and similarly for the value of or the potential across this VDS is applied with V sign rather than a VDC here. The reason for changing this to V sign is that we are going to evaluate the output impedance using the AC analysis. Okay. Now as we discussed in the first experiment, the AC magnitude in this particular V sign is being set to 1 volt, and the DC voltage is set to VDS. Okay, yeah. So having done this, we can actually go on to the AD window, which has already been opened, and I have defined the channel length to be 180 nanometer, and VDS and VGS DC values to be 0.9 and a width of 10 micron. And an AC analysis has been called here, where we are trying to have the frequency within the range of 1 Hz to 1 gigahertz. So in the previous experience we were using 100 mega, so where capital M was used. In this case it is 1 G, capital G is being used to represent this gigahertz. Okay, and under the output section where we are interested in the y-axis, we are trying to plot the current by selecting the drain node of this transistor. So the entire circuit setup is as similar to experiment number 1. The only thing that we have to do is to run this, and the run has created a graph for us which is I by V, where V is basically equal to 1, and now what we wanted is to measure the output impedance, right? So in order to measure the output impedance, we needed a V by I term, which means that we have to plot an inversion of this graph. That could be done by going to Tools, Calculator, select the graph that has been plotted, and go for 1 by X function and then replot it. So this replot, which has been marked with yellow color, will give us the output impedance of this particular circuit, okay, which is basically R naught, and the value that we are getting is around 5.7 kilo ohms. Okay, so one stands here for a voltage, so it is a ohm here. So now this is the value of impedance that we are getting for a length that is equal to 180 nanometer. So now what we do is that let us try to plot it for different channel lengths. Okay, so one could use a parametric analysis to plot different channel lengths, but what I would do is basically go here and change this to 500 nano, and then replot this same graph, and then again perform the same function, which is and then when we try to measure, you could see that from the previous value, the value right now currently we are getting is 38 kilo ohms. So the value has certainly raised to a very large value. Now finally we'll just go ahead with changing the value of length to 1 micron and see whether the impedance rises or lowers. So let me try to feed in the value of 1 micron and then replot it and perform the same action. And now when we try to measure, you could see clearly that the output impedance has risen to a very large value than compared to the 180 nanometer length. So the study of output impedance for different channel length is meant to ensure that the output impedance basically rises with increase in the channel length. Okay, so that is the major objective for this particular experiment. Okay, so we found that using a channel length of 1 micron is always preferable when we design a current mirror, just because it has a higher output impedance, and any current source should have an output impedance which is ideally supposed to be an infinite, but it's supposed to be high, right? Yeah. So with this study, let us fix the value of length to be always 1 micron, and let us try to perform the basic current mirror analysis, where we try to again evaluate the same output impedance as well as try to measure the region of operation and try to find what is the minimum output voltage that the transistor is supposed to have in order to ensure that the transistor stay in the saturation regime. So let me just try to open the basic current mirror schematic. So this is a schematic of a basic current mirror, and the circuit setup is the same, like where the length is fixed to 1 micron and the width is fixed to 10 micron for both the transistors. So one would expect a current value of 100 micron to be excited on this particular node ideally, but theoretically let us try to see what current is passed on across this particular transistor NM0. Okay, so let me try to show you the properties of this. Again, the DC voltage is being marked with, okay, let me just write it as VDS for the DC variable, and the AC magnitude is again same 1 volt here. Okay, so let us click on check and save and then launch our ADL. Now in this, let us try to collect all the variables that we have defined, and the default value that we are going to provide is 0.9 basically, and let us try to evaluate a few things here. Okay, so click on these outputs to be plotted and select on this drain and perform an AC analysis, choose and then AC analysis from 1 to 1 giga. Okay, just click OK and then try to measure. It's supposed to have the same similar reading. Let us try to invert the graph. So clearly you could see that there is a quite increase in the value of this output impedance, which is closer to 300 kilo ohms, and the reason for this is that the value of VGS that we have provided is different from what we have provided in the previous experiment, right? So the value of VGS is basically derived from the current that is being pumped on into the diode connection, and it generates a particular value of VGS, and that is being copied over here. Okay, and that's the reason why we have a different value of output impedance at this particular point. Now the next important thing is that we have to perform a DC analysis in order to measure the region of operation or the VO minimum, as well as to measure the current, okay, at VO minimum. Now let me disable this option of AC analysis and then go to the analysis and choose and click on DC, save DC operating point, component parameter, select the VDS, click OK, and then sweep those variables from 0 to 1.8 and click OK, and that's it. So now let us try to first run this analysis, DC analysis, and that should generate a graph which is similar to our first experiment. And again, if you want, you can just measure the slope of it using the same analysis technique that we have followed earlier. Now the main reason for this plot is to see what value of VGS is being applied across this transistor. The value of VGS is not 0.9, but rather it is 724.8 millivolt. Okay, so that is the voltage that we are applying across the VGS of this current mirror. Yeah, so now let us try to see when the value of VDS is varied from 0 to 1.8 volt, which are the regions that this particular mass transistors are being pushed on. Okay, so in order to do this, we have to get into our ADE, go to outputs and click on setup, and under this you can just give a region of operation as ROP and click on this open to open the calculator, and you have to select this OPT or operating point transient radio button. So once you select, we have to choose the transistor, which is NM0 in my case. So once you choose, we have to look for the term which is known as region. So select this region as the parameter, and this parameter is the one that we need to copy back to our output setup expression. So click on get expression and click add and click OK. Now from our previous semester, we know that whenever we define an output through expression, it is not possible to draw the graph just by running this play button, right? So we have to go for a parametric analysis. So click on this tools, parametric analysis, and right now the variable that we are going to vary is this VDS. Okay, so we will be varying this from 0 to 1.8, and you can choose this as a linear step, and let us vary this in steps of 0.1 or 100 milli. Just click on run. Yeah, so clearly you could see that this is the region of operation, and the region 2 basically denotes that we are in the saturation regime, and region 1 basically denotes that we are in the linear region. And obviously you know that what would be the region 0 mean over here. Okay, so I'll leave that to you. And in this case, the way that we are going to measure the minimum voltage is to look for this 2 that is ending here towards the left. Okay, so what one could do is, by making use of the cross function, one could evaluate the minimum voltage, or you can use the horizontal axis and move this horizontal axis to 2, and if you just hover your mouse, it is almost closer to 300 millivolt, and that is the reading that you could see over here. Okay, so the VO minimum that we are currently having here is 300 millivolt. Okay, now under this condition, we have to know what is the value of current that we are getting at 300 millivolt. Okay, so let us try to replot the DC analysis with the first option of output being enabled. Okay, now just play this button and let us try to evaluate by placing the vertical scale to 300 millivolt. Okay, and try to measure the current, output current, that we would have when we operate the transistor at the minimum output voltage. Now clearly you could see that this current that we would get is not 100 microampere, but rather it is 95.7. Okay, but in theory we also know that when the value of VDS is same as that of the transistor VDS, okay, so whatever the value of VDS that I have across this particular transistor, if it is same over here, then we supposed to have the same current, right? So the value of VDS that we have across this left side transistor or the diode connected transistor is 724.7. okay, so we will try to roughly push our vertical scale to 724.7 millivolt and see whether we are getting the same current. Okay, so let us do the same thing. So 724.7. okay, yeah, so clearly you could see that when the value of VDS is same, then the current is almost closer. It is closer to 100 millivolt. Okay, so if we go higher, then the current deviates away from this 100 millivolt, and when we shift lower than this value, the current actually reduces. Okay, yeah, so basically the inference here is that in order to mimic the same current to flow across this other branch, we have to ensure that the value of VDS is same for both these transistors. Okay, yeah, So now let us try to do the same analysis for the cascode configuration. So here's the circuit where the entire circuit setup is same as that we had before. We have the same width of 10 micron and length of 1 micron for all the 4 transistors that we have used. Okay. Now in this case, I will just try to show you only VO minimum calculation, and the measurement of the remaining things are being discussed in the lab manual. So the results can be extracted with the same method that we have followed for the basic current mirror. Okay. So I'll leave that to you. Now, having this as our current design, let us go for launch ADL, and then choose this VDS 2.9, and then click on this outputs to be plotted, and select this drain current node of the top cascode transistor, and then under this analysis, go for a DC analysis, save DC operating point, component parameter, and choose this VDS and select the DC, and we will be sweeping the DC value from 0 to 1.8. Okay. So with this setup, let us try to first run this DC analysis, and we would get this particular graph, and what we wanted is to calculate the VO minimum, right? So let us do that in parallel. So go to outputs, go to setup, and again define a variable named as region of operation, and click on open and select the OPT parameter. And right now we have to choose 2 transistors here. So one, the parameter for the top transistor, and the second one is the parameter of the second transistor that are there in the output branch. Okay, so first let me select the cascode transistors and select the region from the list, and let us copy this one into our output expression. Let me mark this one as A, so that the top transistor is generated with the region of operation of A, and click on get expression and click on add. Now similarly, we want a region of operation for the second or the bottom transistor, so B, and now we have to select the other transistor okay. So the other transistor has automatically appeared here because it is NM0 is the instance name of it, and it has automatically updated here. So what I do is I'll just click on this get expression. Okay, it's supposed to be NM0. Okay, so I have just directly modified. Else you can just go to opt and then redo it. Okay, so click OK and then click OK again. And now that we have got these things, and we know that whenever we define an output with a variable, it has to be plotted with a parametric analysis. So go to tools, parametric analysis, and right now we will be running the value of VDS from 0 to 1.8, and we need to change the mode to linear steps and the step size to be 0.1, and just run it. Yeah, so clearly you could see that there's the bottom transistor moves out of the saturation region at a very low value of VO, but the top transistor, which is ROPA, moves away from this saturation regime at a much earlier voltage. So again, with the same basic process, we need to know at what value of VDS the transistor is moving away from the saturation regime. Okay, so the minimum voltage is basically a voltage for the cascode such that both the transistors that are there in the output branch stays in the saturation regime. So if we just eyeball it, you could see that the minimum voltage that we have to maintain for both the transistors to be in saturation is around 1 volt. Okay, now what we do is that let us try to get back to our ADE and then enable this ID versus VDS graph, and we are not interested in the ROP values, but still fine. Okay, so when we try to plot, the only thing that we are concerned is that let us try to mark a vertical scale and push this particular vertical scale for a DC value of 1 volt, and clearly you could see that the current that we are getting or attaining from this minimum voltage is around 99.97. Okay, so this is how we measure the VO minimum for a cascade structure. So and there is again a third current mirror structure which is given in your manual. So I would advise you people to carry on the similar set of experiments that we have done for the basic current mirror in order to do the experiment. Okay, thank you.